So I'll share my screen. So is my screen visible?
Yes, sir.
Yeah. Okay. So we'll get started. So basically, in last class, there was a request from the class that I we should look at pumping lemmas. So this is in theory of computation course, and pumping lemma is a tool that we use for proof by contradiction. So we will contradict if a language if a language should be if a language is regular or if a language is context free, right? So so firstly, let us look at some concepts about pumping lemma. First thing you should understand is pumping lemma will only tell if a language is not part of regular language, or or maybe let me start with two types of pumping lemma, right? So yeah, I'll set the base, then we'll go to the concept. Okay. Yeah. So pumping lemma in TOC, there are two kinds of pumping lemma. One is for regular language, and other is for context free language. Right now, this pumping lemma is a concept that you will use to tell if a given language is not regular or if a given language is not context free language. You cannot use pumping lemma to show if a language belongs to regular language, but you can use pumping lemma to show a language does not belong to regular language. So what does this mean? If for example, so let us see what is let us recall what a regular language means. So a regular language is any L that is accepted by a deterministic finite automaton, right? In last class we saw how to construct DFA for a given language. Now can the class say if 0 power n 1 power m is regular?
No,
Yeah, so by 0 power n 1 power m, let me say n greater than equal to 0, m greater than equal to 0.
this is not regular.
This is not regular. Why?
Sorry, both n and m different, right?
Yes,
Yeah, it is
it
regular.
is regular, right? So what I'm saying is you cannot use pumping lemma to show that there is a DFA for this language. But let me give you one more language, 0 power n, 1 power n. Is it possible to construct n greater than equal to 0? Is it possible to construct a DFA for this language?
No,
No, right? So now, I think Shashikant says no, right? Maybe he's saying no based on his intuition. That we cannot construct a DFA with finite states that will accept this language. Now, in this class, for those languages that are not regular, we will see how can we say no in a principled manner. This class is not about saying yes. Yes, we don't know how to say yes yet, but if a language is not regular, we can definitely say no. Okay. So similarly, there is another version of pumping lemma for context-free languages, right? So last class we saw about DFA. I assume that you know context-free language, so we'll look at the definition of context-free language. Then we'll proceed to pumping lemmas, both the versions of pumping lemmas. So now let me begin with what is a context-free language. So these are some excerpts I took from Wikipedia. So this is just a recap of what a context-free language is. So a context-free language is nothing but a language that is generated by context-free grammars, right? So and one of the most famous use case of context-free grammars is to parse arithmetic expressions. right? So an arithmetic expression is an expression of type, let's say 5 plus 10 minus 10 by 2 plus 3 plus 2, right? So you have this parenthesis. Now you can parse this expression using context free grammars and arrive at the result in an unambiguous manner.
So in insertion parsing in compilers.
Yes, that's right. Next, so here earlier I said context-free language is anything that is accepted by a context-free grammar. Now, what is a context-free grammar? So when I asked you a question, what is a DFA? Sorry, what is a regular language? So you tend to answer that if a DFA exists for L, sorry, if a DFA exists for L, then that L is regular. Now, similarly, what is a construct that is required for us to claim a language is context-free? Right? That construct is called a push-down automaton. If you are able to construct a push-down automaton for a given language, then that language is context-free. Context-free. Now, if you have a push-down automaton, which means you can parse the language in an unambiguous manner. One example I told you was arithmetic expressions. Right? Now, so in this slide, for at least for the scope of this class, I want you to have this concept in back of mind. A push-down automata is tightly related with a data structure called a stack. Right? What is stack? A stack contains elements, and the elements arrive in last in first out order. Right? When you push an element to stack, you will push at the top of the stack. When you pop from a stack, you will pop the topmost element in the stack, and you only have visibility to the topmost element. Like now, for example, now you can only get to observe A. You will not get to observe the remaining elements in the stack. You can only observe the remaining elements once you pop out A. Right? So you need to have this stack data structure in the back of your mind. Now, so basically, what we are saying is in DFA, given a language, you see the symbols one after the one, and at the end of consuming all the symbols, if you arrive at a end state, uh, the string is accepted, right? So basically, a DFA is some kind of a construct like this, and you have transitions defined for let's say 0 and 1. This is for 0, and for 1, let's say it's a self loop, and this is a final state. Now, if I give you a string, for example, 0 1 0 1 0 1, if I give you this string, what you will do is you will consume the symbol one after the other from left to right, and you will take transitions according to the DFA. Right? As you see the last symbol in the string, if the transitions take you to this final state, then basically you accept the string. Now, if you see here, apart from this DFA, we do not have access to any other special data structure. In pushdown automata, when you parse the string from left to right, you can get to see the transitions defined by the PDA. In addition, you can also exploit a data structure called stack. This stack you can use to push or pop whatever you want. Right? Now, as a canonical example, maybe I'll just briefly cover context free language with an example, then we'll go to pumping lemma directly. Okay, so let me add a couple of slides. Now, when I say so, this is only for intuition. So, when we say language L equal to 0 power n, 1 power n, such that n greater than equal to 0. This we know this is not regular. Shortly, we will see how to prove this language is not regular, but this language is context free. So, intuitively, how I would solve this question is can I enumerate strings of the language using a stack? Right? Now let me give you a procedure. I'm not constructing a context-free grammar, but I'm telling you an intuitive procedure to see how we know a language is context-free. Right? Now I start with an empty stack. I'm just telling the parsing procedure. Right? So you are given the string, let's say
I,
0011.
I have a query. I have a query.
Yeah,
Even both the pumping lemmas is considered for proving that a language is not
not
concept and
correct.
not regular.
That's right.
But they are not used for that is regular or it is
Yes,
irregular.
it is not useful to answer if a language is regular. It is useful to answer a language is not regular. I'll tell you why this is the case.
Okay, thanks.
Okay. So this slide is only for you to recap a CFL intuitively. We are not going into the formalisms of context free grammar. So this language, I'll show you how to accept strings of the language by using a stack. The procedure that I'm going to follow is for this language. Whenever I see a 0, I'll push it to stack, and whenever I see a 1, I'll pop out from the stack. Right? When I consume the entire string following this procedure, if the stack is empty, then I'll accept it. Right? It is a lack of a data structure like this in DFA. It makes the case that this language is not acceptable by DFA.
So in such a state means any language which have kind of mirror image,
Correct. That's right.
they will be context free. Otherwise, if there is no mirror image, then we
But
we
let
accept.
me convince you that so let's take 0 par n, 1 par n, 0 par n. Let me take n equal to, let's say for n equal to 3 2 for example, right? Then the string is 0 0 1 1 0 0. This string also has a mirror image, right?
Yes.
But can you accept this using a stack? Can you give me a procedure that uses a stack to accept this kind of strings?
Uh, I think I don't feel it good because there are two similar symbols 0 0
Sorry.
because the initial two symbols are similar. So I mean, how we can pop and push? It should be
Yeah,
0 0.
that's the point. So this language is not context free. So why is it not context free? Let me propose a procedure, right? To kind of and let us see if it will accept the strings of the language. Whenever I see a 0, I push. Fine. Whenever I see a 1, let's say I pop. Right. When I consume 0011, the stack is empty. Right. Again, when I see a 0, let's say if I will push, I'll push the stack, push zeros to stack, but I have lost track of this number n by the time I pop it from the stack. Do you see what is happening here?
Can you please repeat, sir?
Yeah. So I'm telling you a procedure. I'm constructing a procedure. Maybe it is wrong. Maybe it is right, or maybe it is wrong. So what I'm saying, given a string of the form 0 par n, 1 par n, 0 par n, my procedure is whenever I see a 0, I'll push to stack.
Okay.
Fine. And whenever I see a 1, I pop from the stack.
Okay.
If I follow this procedure, once I consume this part of the sentence 0 0, then I have pushed to stack, so my stack contains two zeros. Now
Right.
as I see once, what should I do? Should I pop or should I push?
No, you have to pop.
I have to pop. So if I pop as I see once, then basically once I consume these four letters, four symbols, my stack is empty.
Yeah.
Now what should I do when I see a 0? Should I push or pop?
Then you have to push.
Push.
Because,
I am
but
pushing. Now so now what is the decision rule? If your stack is if you let's say now your stack configuration is like this, and what is the earlier I told for this language 0 parent 1 parent, once you consume the symbols, if stack is empty, then I
but
accept.
here, because last two zeros will not make the stack empty, because we
Yes,
are not
so so if you take a decision rule that if stack is not empty, then you'll accept. That is not a right procedure. Reason
no
is
no. I'm saying, because we are not getting one after the zeros, last two
correct,
zeros.
correct, correct. That's
That's
the
why
point.
it can't be satisfying the condition that there is a there is a pushdown automata for
That's right.
this language.
That's right. So if a language has strings that are mirror images, it does not mean it is contextual.
But
Yeah. So now we'll move to pumping lemma. First, I'll state the pumping lemma for regular language. Then we'll solve perhaps two questions in regular languages. So let me state the pumping lemma. So as I told, this is a test for L not belongs to regular language, right? So which means the proof that we will take is proof by contradiction. So I think both these statements will make sense once we see examples. For now, just bear with me and let us try to understand the lemma, the statement of the lemma. Right now, for both the versions of pumping lemma, you have something called a pumping constant. Right now, we will use this pumping constant to prove by contradiction that a language is not regular. Right now, we'll see how to use pumping constant. Now, first, because it is proof by contradiction, the first step is you assume that L is regular. Right? What pumping lemma states is, if you take a string W that is accepted by L, then you can always decompose W into three parts. W equals X, Y, Z. That is a string W that is accepted by any regular language can be broken into three parts X, Y, Z, such that the middle part Y should not be equal to epsilon, or equivalently length of Y should be greater than 0. Right?
I mean, there must be three parts.
There must you can split the string into three parts.
Yeah, because, and if y can't be zero, then there must be three parts. I mean, you can't have this for two parts.
You can make Z equal to epsilon. Nobody is preventing you
Okay.
from making Z
Okay.
equal to epsilon.
Okay.
Okay. So the second condition is the length of xy should be less than equal to n. So by n I mean the pumping constant here, right? And third is for all k greater than equal to 0, it happens that x y repeated k times z is also in L. So did you understand the statement of the lemma?
Can you explain the last one?
Yes. So this maybe we'll take we'll see with the example. But otherwise, do you understand the at least lemma at like
Yeah.
intuition
Yes.
level?
Yeah.
So what this says is, if a language is regular, and if somebody gives us a string that belongs to the regular language, we can always partition W into X, Y, Z, and the conditions are Y should not be equal to epsilon. The length of X, Y combined should be less than equal to the pumping constant that you choose. Right now, if you partition W into X, Y, Z and pump the middle portion any number of times, then the resultant string should also be part of the language. Right now, for example, let us take 0 par n, 1 par n. So we know that this language is regular. N greater than equal to 0, 1, m greater than equal to 0. Okay, we know that we know that L is regular, right? What? So let me take a let me propose a partition scheme. So maybe to kind of avoid ambiguity, for the rest of the examples, let us preserve the symbol n for pumping constant only. So this I'll make it L. Right. Now let's take a string w equals 0, 0, 0, 1, 1, 1, 1. This is a part of the language. Why? Because L equal to 3, this is greater than equal to 0, M equal to 4, and this is also greater than equal to 0. Now, because this is a string that belongs to a regular language, we can partition into X, Y, Z. And let me take the pumping constant n equal to 3, let's assume. Right? Then, let me propose a partition scheme, X equal to 0, 0, Y equal to 0, Z equal to 1, 1, 1, 1. Right? Are you all convinced that X, Y, Z together constitutes W? W will be equal to X, Y, Z. Right? Now, what does pumping mean? Pumping means that you repeat the portion Y 0 or many times. When k equal to 0, you repeat 0 times, that is, you substitute y equal to epsilon. When k equal to 1, you repeat y exactly one time. And when k equal to 2, you'll repeat y two times. Let us see what will happen if k equal to 0. If k is 0, w will be 0, 0, 1, 1, 1, 1, because y is repeated 0 times. If k is 1, you get back the original string that we took. That is, w will be 0, 0, 0, 1, 1, 1, 1. If k is 2, you repeat y two times. W will be 0, 0, 0, 0, 1, 1, 1, 1. Right? Now, this is a regular, we started with a regular language, and I proposed a partition scheme, and I claim in by virtue of pumping lemma that no matter how many ever times you pump y in our partition scheme, the resultant string w is always a part of regular language. Now, do you get
The,
the statement?
the third string is not regular. I think.
Why is it not regular? Because here L is equal to 4 and M is equal to 4.
Yeah,
So L and M are both greater than equal to 0, right?
yeah.
So then this string is part of regular language. Do you get the point? Do,
Then it should belong at 0 power n and 1 power n, which is not
no,
regular.
no. So why is it not regular? So here all I'm saying is L is defined as 0 power L, 1 power M. Nobody is saying as L equal to M. Nobody is saying this constraint.
No, I have confusion because this can be an example of 0 power n and 1 power n, but here L and M are equal actually.
No, no. Yeah, I got your confusion. So what I'm saying is 0 power N, language 0 power N, 1 power N is not regular, not a regular language, because accepting, you should only accept 0 power n, 1 power n, you should reject all other 0 power L, 1 power m, 1 power n where L is not equal to m.
But here, you see that there is L and M both are equal. So,
Yeah, both can be equal. Why is it so? Yeah, basically for 0 power n, 1 power n, this language I cannot construct a DFA.
so that's my confusion because that third string is actually an instance of this language 0 power n, 1 power n.
Okay, let me convince you by drawing DFA for by drawing the DFA for this language. 0 power L, 1 power m, L is greater than equal to 0, m is greater than equal to 0. Right? The DFA is very simple, right?
Yeah, this can be done because
Yes,
here L and M both are different, right?
yes.
But when both L and M are equal, then according
Yeah, why it is not a problem, right? As long if you construct a DFA, then the language is regular.
On that ground, we can also say that we can construct a language for 0 power n, 1
Yeah,
power
how
n.
do you construct for 0 parent, 1 parent? Can you tell me the DFA? You start with zeros, you will consume zeros.
Because I'm saying, the third string which you are explaining,
Hmm.
where 0 and 1 have 4 0 and 4 1, saying that this is
Okay,
regular.
so okay, let me ask you a counter question. Is the language 0 star 1 star regular? Is it regular? So is this language regular?
I don't know.
So 0 star 1 star, we saw it in last class, right? Um, or maybe let me make the language even more simple. Um, so let me make the language 0 plus 1 the whole star. This language we saw last time, right?
This is right.
This regular. Can you tell me the strings accepted by this language?
This can be 0, epsilon 0 1, uh, 0 1,
Yes.
uh,
0 1 0 0 1 0 1 1
yeah,
0 0 0 0 1 0 etc. Right? So
yeah,
this language accepts almost every string, and if you see this language also accepts 0 parent 1 parent,
yeah.
right? So the intuitively 0 parent 1 parent is not regular because we are forcing the this language to reject the strings of type these things. So in some sense, for this language, constructing the dead state, that's the last, do you remember that we had a 5 state, right? So if you want to construct a DFA for language 0 parent 1 parent, the number of 5 states will go to infinity.
Which can't be handled by a regular language.
Correct, because a regular language by definition should have finite states in the
Finite.
DFA. Do you at least intuitively understand why this language is not regular but this language is regular?
Yeah, I got it.
Yeah,
You can say that a particular instance of a language it can be regular, but we only consider the terms in finite extension.
correct. No, if the states are infinite, then that is not a DFA.
No, no, I'm saying that if I say 0 power 4 and 1 power 4,
Mhm.
then which seems to be an instance of this 0 power and 1 power n.
Yes, it is an instance. For example, here a 0 parent, 1 parent, this language has 0, epsilon, then 0, 1, 0, 0, 1, 1, etc.
But
Right?
that is regular.
This is irregular, right? This is not a regular language.
No, no.
Huh.
In previous example, you were saying that
This is regular, but one thing you should notice is let's call this language L prime. One thing you should notice is L prime is a subset of L. The strings that are accepted by a not regular language can be a subset of regular language.
okay,
Because see the universal language, right, that we saw last time when we designed complement of a language, we constructed a notion of universal set omega. Do you remember? So that universal set was indeed we can construct a DFA for that universal set. And what was the universal set? We saw that the start state will be the end state, and you will have self loop transitions for all symbols belonging to the symbol set.
I have considered in last slide you were explaining that the third string which is uh, zero that 4 zeros and 4 1s, that is regular
Yes, this
because this is
no no
an
no. And this string is part of the regular language.
okay,
This string is a part of regular language.
okay. So we should not see this an instance of 0 power and 1 power n.
Yes, at least for this question, you should not see it as an instance of 0 parent 1 parent. For this question, the language is 0 parent 1 parent.
Okay.
Yeah, I think I get your confusion, but just think about it. Maybe after the class.
Okay, got it. So
Oh, you
this
got
is
it. Nice.
this is a superset of
Correct,
zero.
correct, correct. That's right. That's right. So this L is a superset of this 0 parent 1 parent, and this L is regular because you don't need to have many null states in
Okay,
some sense, right? That is
okay,
why this language can be represented by finite automaton,
okay,
as opposed to this language that demands many null states.
okay, got it.
Okay.
Thank
Yeah. Now we'll look at the questions, right? I'll go to the questions uh, here. So maybe we'll take questions 1 and 2. See, maybe you can take it as homework. Okay. So first language is 0 parent, 1 parent, 2 parent. Second language is WWW. Let me copy the questions. Yeah. So these two questions are to show if a language is not regular. So question is, use pumping lemma for regular languages to argue first 0 parent, 1 parent, 0 parent, 1 parent, 2 parent, right? Yes,
you. Yeah,
0 parent, 1 parent, 2. Sorry. Yeah. 0 parent, 1 parent, 2 parent. So as I told you, I'll refer the symbol n for the pumping length. So I'll change the question to be 0 power 0 power m, 1 power m, 2 power m, such that m greater than equal to 0. This is the first question. And second question is w, 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 such that is there a constraint on length of w? No. So, sorry. Yeah, www, such that the string, the symbols of the languages a comma b whole star, right? These are the two questions. Now we will use the pumping lemma that we just saw to show that these two languages are not regular. Is the question clear to everybody?
yes,
Yeah. So as I told you, we will prove by contradiction. So the first step is to assume let's call this L1, let's call this L2, right? Assume L1 equal to regular, right? Now because L1 is regular, the pumping lemma says that there exists a pumping constant. Pumping constant n greater than equal to 0. Sorry, I'm not very sure if n should be greater than equal to 0 or 1. That please verify. But nonetheless, you have a pumping constant n, right? Let's maybe for this example, let's take n uh, greater than equal to 1. This I'm not very sure. It is either greater than equal to 1 or 0. Okay. There exists a pumping constant. And if you take a string that belongs to L1, you can partition W into three parts X, Y, Z, and you can pump the middle part K times arbitrarily K number of times, and K should be greater than equal to 0. Right. Now, given a pumping constant, let me choose W equals 0 power n, 1 power n, 2 power n. Okay. So now can you propose a partition scheme W, so not W, right, X Y Z. Can you propose a partition scheme X Y Z such that X Y par K Z is always a string of L1? That is a question. And pumping constant is n. Now the first question is, can Y can first question I ask is, can Y contain 0, 1 and 2? Can y contain all the symbols 0, 1 and 2?
Yes, it's possible.
How is it possible?
No, no,
Huh.
it's not possible
It's not
because
possible. Why? For example, let me take n equal to, let's say the pumping constant were
we
2.
can exclude to the power, I mean,
Correct.
the constant 2, but
Yeah.
not 0 and 1.
Correct. So let me take the pumping constant. Let's assume pumping constant were 2. If it were 2, then W will be 0, 0, 1, 1, 2, 2. Right. Now we saw a condition that x, y together, length of x, y together should be less than equal to the pumping constant n. Right. Now for the sake of argument, let's say you assumed x equal to epsilon. Right. Then at most you can accommodate only 1 and 2, because once you accommodate this 1 and 2, you have exhausted the pumping length n. Right. For you to consider, for all the symbols 0, 1 and 2 to be part of the substring y, you should at least consider 0, 1, 1, 2. But you cannot do this because here the length of y will become 4, which is much greater than 2. I hope you got the point why y cannot contain all the all the symbols 0, 1, 2. Is there any doubt so far?
No,
Yeah. Now, once you kind of digest the fact that y cannot contain all symbols, if you pump y, right, not all the symbols get pumped,
yeah,
right? And that is why the pumped string. So now you pump y for any k greater than 1 times. If you pump y for any k greater than 1 times, you see that you get a w. Let's call this pumped w maybe. Pumped w is not part of L1, right? But the pumping lemma says that if L1 was regular, the pumped W will also be part of the language. That is why we are contradicting pumping lemma. That is why we are contradicting pumping lemma, and that is why this language of the form 0 parent, 1 parent, 2 parent is not a regular language. Is the proof clear to all? Is there any doubt?
no,
Yeah. So now I will. So earlier there was a question, right? Why is it the case that pumping lemma can only be used to show a language is not regular, and it cannot be used to show that a language is regular? Can somebody, just look at the slide? Can somebody point out a step that I used in the proof that makes pumping lemma qualified only to inspect not belongingness of a language? Okay. So the step that is crucial is this step here. So to prove a contradiction, I took a subset of the I took a subset of overall strings acceptable language. Right. In general, I took strings greater than equal to pumping length. So I did not. So what I'm doing here is I'm taking one particular W and I'm showing the contradiction of pumping lemma, right? But for pumping lemma to kind of be qualified for acceptance also, you should verify this property for all strings in the language. Do you get why a pumping lemma cannot certify if a language is regular?
yeah, got it. Because you can't have this for all the languages.
Yeah, correct, correct. So you cannot go over all the strings in the language one after the other and check, and check if you have a partition scheme that will make pump W also part of the language. Right? To prove a contradiction, you just take one string of your choice that qualifies the pumping length property, and you show a contradiction. That is
Yeah, which
how pumping lemma will certify not belongingness, but not the belongingness of a language.
checking is possible for for few instances, but not for every instance.
Correct, correct. Okay. So now maybe in the class, can you take the second question? L2 equals W W W such that W part of A comma B the whole star. Right. Now I will give example example string for this language. Let's assume W equals AB. Right. If W equals AB, then this string is nothing but AB AB AB. I'll give you 2 minutes. Just try to solve this question using pumping lemma. Maybe I'll give you a scheme of the proof. Then you fill the dots for me. Fine. The first step is assume L2 equals regular. Fine. And let's say pumping length is n. N. Okay. Now you will take a string W W of whatever form you want. You take any string of your convenience, right? But this string should necessarily belong to language L2. Now, once you take a string of your choice, you will see if there is a partition scheme that will make W into X, Y, and Z such that the length of XY should be less than equal to the pumping length N, and the length of Y itself cannot be 0, right? And you will see for the string that you you will see if there is a partition scheme that will make X, Y par K, Z also part of L2. Okay, so does anybody have a proposal for W?
So we can take BA as Y.
No, no. Your proposal should be generic enough to accommodate the pumping length N. N can be any natural number. So when you say BA, then your proof is restrictive only to this string. But pumping length can be arbitrary. Do you understand what I mean?
Yeah, got it.
Yeah. So
We are
let us take your string only, right? Now to make your string, to accommodate with this pumping lemma construct, let me take the string b par n, a par n, b par n, a par n, b par n, a par n. Are you convinced that this string belongs to the language?
yeah,
And
belongs to.
yeah, and so I am just taking the string that you proposed, but in addition to your proposal, we are also accommodating the pumping length here.
Yeah,
Got a
got it.
difference? Now check if a partition scheme exists for this string of the form b parent, a parent.
So we are basically taking a general case rather
Hmm.
than specific
Correct,
case.
correct, correct. Now for the general case, check if you have partition scheme x, y, z. So actually, this proof is very simple, right? So you can let's say you take y as a one thing is you cannot take y equal to w. So by w I mean okay, I think symbols are confusing. So let us call this as w prime. W prime is equal to w. Okay. Now y you cannot take w because length of w itself is 2n. है ना? So you can only take y as a substring of w.
Can you repeat that? And
Yeah, you cannot take y equal to w because the length of w itself is 2n. So L2. So here I have changed the symbol. So I'm calling the strings that belong to L2 as w prime, and w prime is of the form w. Right now, what is w? W is b power n, a power n, and pumping length is n.
saying that this length is 2n.
Yeah. So what is length of w? What is length of b power n, a power n? You have n b's and followed by n a's, right? So length of w is 2n, right?
Yeah.
Length of w is 2n. Now what I am claiming is you cannot make y equal to w. Y is always a subset of w.
Okay. Got it.
Right now, if you take y as a subset of w, you can basically enumerate cases and show that the w prime that you obtain by pumping y will not belong to L2. I think this part is easy. Why? Because in y you cannot take like total w so that you can pump w. So the resulting string will also have w constant. So rest of the proof, will you be able to complete?
Yeah.
Yeah. Okay. So then the third question there, please take it as homework. We'll move to the pumping lemma for context-free languages.
Because I want to say, because if we get y equal to w, then obviously we can't have the string w because there will be
Correct.
an amount
Correct.
of
Correct. Correct. That's right. Okay.
yeah, but
Yeah. Now we'll go to pumping lemma for context-free languages. So here again, so I think by now you are familiar with how to employ pumping lemma. I'll directly go to the statement. This is kind of more complicated than pumping lemma for regular languages, right? So here again, this is for certifying that a language is not context free. And how you'll certify? You'll prove by contradiction. So the first step is again to assume that a given language L equal to context free language, right? First you'll assume this. Then what pumping lemma states is if a language L is context free, you have a pumping constant n. So like earlier, we also have a pumping constant here, pumping constant n, and for given any w, any string that belongs to the context free language L, you can partition x into five parts here. Earlier we partitioned into three parts. Here we'll partition into five parts: u, v, w, x, and y. Right? You will partition into five parts, and the condition is length of vx is not equal to 0. V can be epsilon or x can be epsilon, but v and x together cannot be epsilon, right? And second condition is, yeah, so this pumping constant n should be greater than equal to 0. Earlier I was telling that I'm confused if it should be greater than equal to 0 or greater than equal to 1. So it turns out that pumping constant should be greater than equal to 0. Okay. um, and second condition is the length of the string v w x should be less than equal to the pumping constant n that you choose. So earlier what we had the middle part to be, so in regular languages we had the middle part y should be less than equal to the pumping constant. Here again we want the middle part to be less than equal to the pumping constant, right? Middle part should be less than equal to pumping constant. and the left end, both v and x cannot be equal to 0, right? Now the pumped string is going to be of the form u v power u v power I w x power I y. So earlier you pumped y, here you pump the you pump the partition v and x, and both these partitions you will pump same number of times, where I is greater than equal to 0. Okay, I think now you can relate why we have. So here so this pumping lemma is also kind of same only, but we have the weird constraint that vx not equal to 0. Why we have this constraint? Because it should not happen that as you pump v and x, you trivially get w prime. So pumping should have some impact in terms of transforming the string that you pump. To enforce that effect, we
Because
yeah,
I think this is because in CFL we have to take care of two things to check. One is financial automata, and the second is that stack.
correct. So
That's
yeah,
like
that's right. So here in some sense we get a mirroring property, right? So in stack, what you do, seeing some symbol, you either push or pop. So in some sense, what this pumping lemma says is v par I. So you can push v into the stack as many times as you want, because you can still accept the language by means of popping x whenever you see v. Sorry, whenever you see x, you can keep popping v and recover the original string,
yeah. But,
right? So here you pump the portion of the string that you push, and equivalently, or equally, you pump the portion of the string that you want to pop on seeing v. Okay, now I think now that you brought an interesting question, so let me give the language 0 par n, 1 par n. For this language, you can trivially, you can, like you can easily say again. So let me change the symbol. So let's assume the language is 0 par m, 1 par m, right? And given a pumping constant n, what you will take is the string 0 par n, 1 par n. Now you can easily verify that this string can be pumped. And how I will partition? Let's say that u is going to be 0 par half, 0 par n by 2. The first n by 2 zeros I will put it into u. The second n by 2 zeros I will put it into v. W will be epsilon. X will be 1 par n by 2, and y will be 1 par n by 2. With this partition scheme, if you pump u and equally pump v, you can verify that the resultant string is always a part of the language,
yeah.
right? That is the notion of this pumping lemma. Okay, now we'll go to the question. Maybe because we're running out of time, I'll just solve one question from pumping lemma. So the remaining questions also follow, like say, same logic. If you understand pumping lemma for regular, pumping lemma for CFL is not very difficult. Only thing is you have to pump two symbols, v and x. Fine.
Yeah, but
So we'll solve first question perhaps. 0 par n, 1 par n, 0 par n, 1 par n. So L equal to 0 par n, 1 par n, 0 par n, 1 par n, such that n is greater than equal to 0. Right? So I'll change the symbol here also. Let's make the language 0 par m, 1 par m, 0 par m, 1 power m. Right? Let's assume that you are given the pumping constant n. Now can you propose a string that you will take?
we can have uh, 0 power n, 1 power n,
Correct. 0
0 power.
par n, 1 par n, 0 par n, 1 par n. Now can you propose a partition scheme for this string into, so we had
We
UV
already have
UV.
four parts. Easy to.
Yeah. So what are the constraints? There is something. Yeah. What are the constraints? So the middle part cannot be greater than n. That is the constraint. And v and x together cannot be 0. Length of v and x together cannot be 0. Right? Now let us take vxy and argue. So vxy should be less than equal to n. है ना? So now what can vxy contain? Vxy can contain, let's say you can it can contain all of 0 per n, right? Or it can contain, so case 1, vxy can contain all of the beginning portion of the string, right? Or vxy can contain some zeros in the beginning part and some zeros in the first part. So let's say it contains 0 power n minus m, 1 power 1 power m.
So there is a question.
Yeah,
In the first case, when you're saying that all the zeros of initial zeros, then it means that u is zero. I mean,
correct. You can be epsilon, right? There is no constraint on u and z.
okay,
You can be epsilon. So I'm just trying to sketch the proof. So what can vxy together contain? Right. That's what we are trying to sketch. Now, remember that you can make either y epsilon or v epsilon. That is allowed.
we can also have access for
You can have x epsilon, but vx together should be less than equal to n. That is the only constraint. Sorry. Uh, yeah, you can have x also epsilon, right? X can be epsilon, but v and y together cannot be epsilon,
yeah.
right?
Got
So no, so once you take the partition scheme, the pumped string w prime is going to be u v power I, x y power I, and z. Okay. Now, no matter how you choose, how you make this partition, right? I can write the string as u equal to, let's say, 0 power some l, v equal to 0 power 0 power, let's call it yeah, 0 power l, 1 power sorry. So how do we take the string? W will be equal to u. V can be represented as uh, yeah, v can be represented as 0 power a, 1 power b, let's assume. Then x can be represented as, again, so you can start from 0 or 1, and yeah, 0 power a, 1 power b, 0 power c again. And x can be represented as again 0 power a, 1 power b, 0 power c. And y is again 0 power a, 1 power b, 0 power c. And z is anything that we don't care. Okay. So here, what is the constraint? Oh, I think I used ABC, right? So let me call it A prime, B prime, C prime, and A double prime, B double prime, C double prime. Okay, so this is V, this is Y. Are you convinced that this is how the partition scheme will look like? So here you can make A equal to 0, B equal to 0, and C equal to 0. That way, any partition you take, it will fall in this scheme. Right? Now let's pump this string. So W prime will be equal to u. If you pump v I times, you will get 0 power a into I, 1 power b into I, 0 power c into I, and x will be 0 power a prime, 1 power b prime, 0 power c prime. and y will be 0 power a double prime into I, 1 power b double prime into I, and yeah, 0 power c double prime
So
into I.
I'm not getting the partition you have created here.
Yeah, so now you tell me some
I
partition.
am
Yeah,
I'm not capable of relating it with the string 0 power and 1 power
yeah,
and
yeah,
0.
yeah. So let's take an example, right? So let's say 0 0 0 1 1 1 0 0 0 1 1 1. Okay. So now you tell me some partition. I will fit into this construct. So let's say for sake of argument, this is u, this is v, this is x, this is y, and this is z. So with this partition scheme, ai will be equal to uh, a will be equal to 1, b will be equal to 3, and c will be equal to 0. A prime will be equal to 2, b prime will be equal to 0, c prime equal to 0, and
So
similarly,
got it. Got
yeah.
it.
So now if you pump, basically you will get this string. Now we have to take cases for like for we have to instantiate ai, bi, ci, abcs, and we have to argue that this pumped string w, we have to construct a string such that this w prime will not be accepted by the language here, no matter what scheme of partition you take. Now here you cannot take arbitrary a b c, a prime, b prime, c prime, a double prime, etc. Now you have to incorporate the constraints here. What is the constraint? Length of v and y should be less than equal to n, right? Sorry. Uh, uh,
The constraint
so
is
yeah, a plus b plus c, a prime, b prime, c prime, these together should constitute less than equal to n, and length of vy should be less than equal to, cannot be equal to 0. That is a plus b plus c plus a double prime plus b double prime plus c double prime. This cannot be equal to 0, or this should be greater than equal to 0. Sorry, greater than 0, and sum of all the constants like a plus b plus c plus etc plus c double prime should be less than equal to pumping constant n. You got the idea of the proof? You understood the constraints, right? Is there any doubt with the constraint here?
can you repeat one?
Yeah. So firstly, are you convinced that w can be once you partition w, this is how the string will look like? Are you convinced with that?
Yeah.
There is no confusion there, right?
No.
Yeah. Now we have to incorporate the pumping lemma constraints. What are the constraints? Length of Vx should be not equal to 0, or length of Vx should be greater than 0, and length of Vxw should be less than equal to n.
Yeah.
Now in our partition, what is length of, sorry, what is the length of what is the length of v and y? Sorry, v and x, right? Is it v and y or v and x? Yeah, v and x. Okay. So this constraint represents v and x. Length of Vx should be greater than equal to, greater than 0.
Okay.
Right. So what is length of Vx? It is a plus b plus c plus a prime plus b prime plus c prime, right?
Yeah.
And length of Vxy together should be less than equal to the pumping constant n. Alright. Now we have to take cases and we have to show that no matter what partition scheme you come up with, you will arrive at a W prime for some k, for some pumping, for some I, where I is the number of times you pump the string. For some I, basically the W prime will not be part of the language.
Okay.
Okay. So yeah, runtime, what I feel is, I think this if you visualize w in this partition scheme, perhaps I think answer will be lengthy. I'll look for a simple answer and I'll solve it myself and paste a link in the excel sheet. Does that
Okay.
work? But nonetheless, I think this is how the proof will go. So here I think I have taken a complicated way of partitioning W by means of representing this way. I guess that there should be other simple ways.
Yeah,
But nonetheless, this is you understood the proof, right? The way the proof will proceed.
yeah, yeah.
Yeah, I'll solve this in a simple manner and I'll post a link maybe in next half an hour.
Okay,
Okay. Yeah.
okay,
So once I post it, maybe I'll write detailed comments. So I request you to take the remaining questions as homework.
okay.
Okay. Yeah. If there are any questions, we'll take. Otherwise, I think we can break for the session.
I just want to know what is mean by A by B.
Yeah, that
Let
question even I did not understand.
let A by B is the third question.
Oh, okay. What they're saying, W such that Wx is in A for sen x in B. Yeah, maybe I'll explain this question, but I don't know maybe how to solve this question.
No, no,
Uh,
I am not saying I don't want to explain this. I just want to know what is the division,
no, no,
A
this
by
is
B.
not
What,
division operator. This operator they are defining. A
okay,
slash B is maybe it's not a standard operator. For the purpose of this question, they are assigning this meaning to the slash operator.
okay.
Right? You cannot take this to be a general operator.
What that symbol means.
In this question, what the symbol means is this language A slash B contains set of all strings W, right? Such that Wx is in. So first, let's take x in B. Maybe I'll go to the slides, right? So can you read out the question for me?
I need to open the page.
Yeah, or maybe that's okay. I'll have an yeah. W such that Wx in A and x in B, where A is a context free language, right? Yes. A equal to CFL and B equal to regular. Okay. This is a question, right?
Yeah,
Now, for the just for the purpose, no, to understand the question, let me take A equal to 0 power n 1 power n. This is a context free language, correct? This is a context free language, right?
yeah.
Now let me take the language B as some regular language. Let us take. Can you tell me some regular language?
0 and 1 m.
0 comma
0 and 1 m.
1 n, where m greater than equal to 0, n greater than equal to 0. Okay,
Yeah.
here n is greater than equal to 0. Right. What are they asking in the question? Okay, they are okay. The question is we'll come to how to enumerate the strings of A slash B, but the question is L context free? That's the question. Now we'll see how to now we'll see what this language means, right?
Yeah,
So
yeah.
what are the set of strings accepted by this language? That is W, right? Now W is a part of L if Wx is part of A, right? W is a part of this language L only if Wx is part of A. What does this mean? Now, so B is regular, meaning corresponding to this B, there is a set of strings, right? That is accepted by language.
So maybe
Let
you
me
would say that there is a string and there is a common part which belongs to both ends.
correct. That's the question. So if I expand this regular language B in terms of strings that it accepts, let's call the string S0, S1, etc., etc. Right now, Wx is nothing but you will take each string in the regular language, that is WS0, WS1, and you will go on, right? Until until you hit a string, let's say WSN, such that WSN is accepted by the context free language A,
Okay.
right? If there is a S, if there is a SN such that WSN is in is accepted by the context-free language A, then you'll accept this W, this string W, by the language L. Got it?
Okay.
Yeah. Now question is, if you construct such a language where A is context-free, B is regular, and you divide this language, or maybe you apply the slash operator, then is this L always context-free? That is the question.
Okay.
Yeah. So trivially, if epsilon belongs to B, right? Then this is trivially context free. Do you see why? If the empty string is a part of language B, then this language is trivially context free. Do you see why?
No, no, no.
No. Okay. Yeah. So let me add a slide maybe. Ah, how do I start from? Okay. So what I'm saying is, let's say B is a regular language, right? Now let's assume that epsilon also is accepted by B.
Okay.
Fine. Now for now you want to construct strings of the form wx, right? Such that wx is accepted by A. A is a context free language. Now, if epsilon is part of B, I will trivially assume x equal to epsilon.
Yeah.
Then what is A minus B? A minus B is nothing but A, right?
Yeah. Yeah.
That is why when if epsilon is part of this language, basically A is trivially context. So A minus B is trivially context free. You know, if
Yeah.
epsilon is not part of B, then you will search for suffix such that W is part of L.
Yeah.
Maybe I
Got
think W such that W. Yeah, I have to think about this question. Yeah, I don't know the solution. Yeah, but I think this is a nice question.
So these are all six microsix textbook.
Sorry,
This is from microsix third edition.
this
The
one.
question.
Oh, this one question is it? For some
Yeah.
textbook.
Yeah. The textbook
Okay,
microsix.
okay, okay. Yeah,
This is a recommended book. Recommendation in MIT also.
MIT. Okay, okay. Yeah, but I think this may be kind of a overkill for gate, because for gate all we need to understand is see, for example, given this language 0 paren, 1 paren, 0 paren, 1 paren, right?
Yeah.
Intuitively, we know that we cannot accept it using a stack.
So in Gate, basically, they want to know whether you can distinguish between the languages, whether
Correct,
regular.
correct, correct. Because it is multiple choice question. They are not asking. They cannot ask you for a pumping lemma proof.
No, sir.
Uh-huh.
Basically, because we are seeing questions like multiple choice questions, so they can give conditions for that, and you have to analyze that particular
Ah,
language.
okay, okay, yeah. But it is good to know these concepts. So these concepts will enhance the thinking process,
Yeah.
but also focus on solving questions. Okay, solving problems.
Okay.
So I have one homework. I will solve A and paste a link to the PDF in the Excel sheet here.
Okay.
Okay. Yeah. So for the tricky part is coming up with the partition.
Yeah.
Once you come up with a partition in a convenient format, the proof will simply follow.
So with the practice,
With practice, it will come. Yeah, yeah. Okay, then. So next class we
Hello,
will
sir.
proceed to linear algebra.
Hello, sir.
Yeah. Yes, JD.
Uh, Sir, I am currently in the first year,
Mm-hmm.
and I want to give a GATE examination. Um, so, is a NPTEL lecturer sufficient?
Yeah, because you're in first year, right? So you have a lot of time. I would say that you should prepare in
Yes.
a principled manner so that you do better in your engineering curriculum, as well as you can prepare for GATE alongside.
Sir, what are the topics to be covered in the first year through NPTEL lectures?
You can start with basic.
So there is a semester semester concept. If we go for check the NPTEL website,
Okay.
it, they already created a section where you can select a different semester what you should proceed for at particular semester.
Okay,
Okay,
okay.
sir.
Yeah. So you are in computer science stream, is it?
Sir, yes, sir.
Yeah.
And
Then I would
sir,
suggest you start with programming and data structures.
okay, sir.
Yeah.
Through
Pra-
YouTube, sir.
Sorry. Yeah, YouTube. You can check NPTEL lectures, or there is this MIT OCW lectures. So many resources. Take a resource that is comfortable for you. Because you are having lot of time, you can prepare in a principled manner. Refer textbooks.
And sir, um, in GATE examination, we have to develop our problem solving skill.
Yes, yes.
So, what book do we refer?
I would suggest previous year questions and are you aware of this website Gate Overflow?
Yes, sir.
Yeah, Gate Overflow is like it's a very mature resource. I would say this is like a boon for students who prepare for Gate in computer science stream.
Sir, which websites are GATE
GateOverflow.in.
or flow
Gate
dot in?
Overflow.
Okay,
Yeah,
sir.
and also they also have a
Sir,
book. They have test series. Like this is a very good resource.
and sir, when we had completed some topic lecture through the NPTEL lectures,
Hmm.
then that where to find the related problems to that lecture.
Yeah. So let me see if there. Yeah, for example, here it is organized by topics, right? So you have, let's say you took algorithms course in NPTEL,
Yes,
then
sir.
you have questions organized through topics. For example, let's say you study DD programming,
Yes.
then you will go to this topic and you will find lots of questions here,
Okay, sir.
right?
Okay,
So
sir.
firstly, focus on because you're in again. So this advice is to you because you are in first year, you have a lot of time. Focus
Yes,
on
sir.
textbooks and parallelly solve questions. As soon as you study a topic, immediately solve questions on the topic, right? For example,
Yes, sir.
let's say you study Dijkstra's algorithm, then there is this question. You have subjects are organized by topics, and here you have tags also, right? For example, if you click on Dijkstra algorithm, you get all the related questions in Dijkstra,
Yes, sir.
right? Maybe it is too much to solve all the questions here, but I am sure if you solve like 4 5 questions in this topic, the concept will become very clear for you.
Yes, sir.
Yeah.
Um, and sir, my JEE examination doesn't go very well, so I thought to prepare for a GATE.
Okay, okay. Yeah. Okay then.
Sir,
uh, Sorry,
when
go ahead.
will be the next session?
So we meet every Friday 6 to 7.
Every Friday, 6 to 7.
Yeah. So from next week, we'll start with
I,
linear algebra.
I have shared Google Drive link which is actually from NPTEL website. You can check that and get a specific course link.
Okay, okay.
Okay, sir.
Yeah. So
Thank you,
maybe
sir.
Jaydeep, maybe you can copy this link, right? So this is
Okay,
organized by
sir.
semester, is it?
Okay, sir.
Yeah.
So, thank you, sir.
Yeah. Thank you. Bye.
Bye, sir.
Thank you.
Yeah. Bye.
Bye.